Okay, done with potential difference. Let's move to EMF. Yeah, I believe we're not strange to that word EMF. Electromotive force. Electromotive force. Okay, when you measure the potential difference across a battery or between the terminals of a battery that is not in a complete circuit, you are measuring the EMF of the battery. That is why the definition, the simplest and clearest definition of an EMF is the potential difference, okay, between the terminals of a cell or battery when the cell is not delivering any current to the circuit. You understand the potential difference? That is what this I know what he's trying to explain here. And when you measure the potential difference between the terminals of a battery that is not in a complete circuit, and I told us an incomplete circuit or an open circuit is a circuit in which there is no resistance, there is no load, there is no load. Okay, so when you measure the potential difference between the terminals of that battery when the battery is not delivering any charge or current around the circuit, you call that electromotive force. So electromotive force is the potential difference between the terminals of a battery when it is not delivering any current to the cell. This is the maximum amount of work per coulomb of charge the battery can do to drive charge from one terminal through the circuit to the other terminal. That's another definition you have there. The maximum amount of work per coulomb of charge a battery can do to drive charge from one terminal through the circuit to the other terminal. Now, electric potential difference is also called voltage. When you measure, I think the first diagram you have up here, you have V and all that. There's no load connected. You have a voltmeter, okay? Then you have battery. If you check the second one below, you see the load, that resistance symbol there. That's the resistance symbol, or you call it the load. When you measure the potential difference across the terminals of a battery or between the terminals of a battery that is in a complete circuit, you are measuring the terminal potential difference of the battery. So you can see the difference between potential difference and electromotive force. For both of them, we are measuring the potential difference of the battery. Why for potential difference? We are doing that when the battery is supplying current to the circuit. Why for electromotive force? We are doing that when the battery is not supplying any charge or current to the circuit. Although this is measured in volts, it is not identical to the EMF. The difference will be the work done to drive charge through the battery. The difference will be the work done to drive charge through the battery. For potential difference, work done is required to drive charge through the battery to the circuit. For electromotive force, a work done, okay, to drive charge within the battery will not be there, because for electromotive force, the battery is not supplying current to the circuit. Okay, then you have that diagram there. You have your voltmeter, you have your resistance, then you see the diagram of a normal battery. If you don't want to use a battery, you are free to use an accumulator for the experiment, an accumulator, or use a normal battery. Okay, one lead of the voltmeter is connected to one end of the battery. You know, you have, if you have seen a voltmeter, you have the one used in the laboratory, you have the red spot and you have the black spot. The red spot, you connect it to the positive terminal of the battery. The black spot, you connect it to the negative terminal of the battery. So one lead of the voltmeter is connected to one end of the battery and the other lead is connected to the opposite end. The voltmeter may also be used to measure the voltage across a resistor or any other component of a circuit, but it must be connected in parallel. Take note, it must be connected in parallel. Let's see that diagram once again. Can you see? It is connected in parallel. It must be connected in parallel to the resistor. So the voltmeter is connected in parallel. It's one of the questions often asked in Jamb. What circuit connection is used for the voltmeter and a resistor? It's a parallel circuit connection. Okay, quickly, current. Okay, we're talking about current. Current, I said earlier in the beginning of the class, is the flow of charges. Yes, the flow of electrical charges. When we talk about current, we talk about how much charge moves past a fixed point in a circuit in 1 second. How much charge moves past a fixed point in a circuit in 1 second. Okay, now think of charges being pushed around around the circuit by the battery. There are charges in the wires, but unless there is a battery, they will not move. Yes, you have a copper wire, there are charges in the wire, but unless, okay, there is a battery, they are connected to a battery. It is a battery that moves the charges through the wire. When one charge moves, the charges next to it also move. When one charge moves, the charges next to it also move. They keep their spacing as if you had a tube of marbles, like this in the picture below. Can you see it? So you have one charges moving. The motion of one charges brings about the motion of the corresponding charges after it. If you push one marble into the tube, one must come out the other side. If a train locomotive moves, all the carriages moves immediately because they are connected. Just the same way, the working principle behind the motion of a train, that is the same working principle behind the movement of charges across metallic conductor. That will bring us to Ohm's law, I think, in the next um, uh, a couple of slides. The next class we'll look at Ohm's law. All right, now the formula for charge for current I equals to Q over T. Current I is measured in ampere equals to Q stands for the quantity of charges or quantity of electricity. Quantity of charges in coulombs. T is the time in seconds. So you have I equals to Q over T, which is quantity of charges over time. So current is measured in ampere or coulomb per seconds. Yeah, coulomb per seconds. Now, the idea is that if a battery started to drive charge in a circuit, all the charges start moving instantaneously. Now, look at this short fact down. You have Benjamin Franklin made a guess about the direction of charge. Yeah, it's one of the things that is still causing disputes in the world of physics and science. The direction of charge. The direction of charge flow when rubbing smooth wax with rough wool. In our secondary level, we did electrostatics. Yes, electrostatics. How charges are produced, how charges are generated. Okay, so when you rub smooth wax with rough wool, it thought that the charges flowed from the wax to the wool, which um um means from the positive side to the negative side. The wool negatively charged, the wax positively charged. Okay, now which was opposite to the redirection. So it thought charges moved from the positive side to the negative side. All right, so due to this, electrons are said to have a negative charge, and this objects what Benjamin Franklin called negative, which means a shortage of charge. Okay, uh but in reality, negative means excess of electrons. Excess of electrons. That is why when someone comes and say charges move from the positive side to the negative side, okay, they'll say they're correct. Some say no, charges move from the negative side to the positive side. So we will now have a dispute, all right? But conventionally, charges move from the positive side to the negative side. Conventionally, uh charges move from the positive side to the negative side. But in practicality, reality, analysis, experiment, we see that charges move from the negative side to the positive side. So if you say both statements, you're correct. Conventionally, charges move from the positive side to the negative side. Also, charges move, reality, practicality, experimentally, charges move from the negative side to the positive side. Why? Because what is current? Current simply means the flow of charges. What is another word for charges there? Electrons, the flow of electrons. And electrons are negatively charged. They are not positively charged.